All right, so here's our first parser that looks for an A and returns a pair of A and the remaining input unmatched. Now, I am the world's worst typist and copy paster, so I've captured the entire console session, and we'll follow it here, but the session is live, and we get to copy paste at any time. Okay? So our first order of business is to handle non-ASCII characters, for example, the Spanish word año for year. Holy October, man. Now, don't panic, because the equivalent symbol is okay, but how many chars do we take into the symbol? Well, forget about it. Well, let's just deconstruct into Boolean, and we notice that the higher order bit for ASCII is 1, the higher order bit for non-ASCII, higher order bit for ASCII is 0, the higher order bits for non-ASCII, come on, they're getting cut off. There we go. All right. So we did some research on Unicode, and we discovered that UTF-8 finally prevailed. It's a variable length encoding, and it leaves ASCII alone. So we go on and we write a little expression using the nifty colon conditional pattern match, it's in the book, to examine the 5 order bits and return how many bytes we should take from UTF-8. Okay, so we seem to be in business here. So we take that expression, we wrap it in a function called grab, which we iterate over a record, new dictionary definition format. It has the input chars and output symbols, non-shared variable state. All right, and now we can take a list of UTF-8 chars and return a list of well-manual symbols. So we're going to parse in symbols. Yeah? So we write our first parser generator that deals with symbols and matches on the first argument. And there we go. Now, that's a good start, but we can't compose because the form of the input and the output are different. So we fix that by uniformizing into a record that has a list of symbols for input and output. Okay, much better, but we're failing silently, and we like an error message. All right, cute curious culture noses. We're going to create a discriminated record, discriminated unit record here, where output and input are on the success side, and error message is on the failure side, and we have a Boolean success flag that tells us which side of the unit we're on. We add a constructor to instantiate this object, and then we realize we can pull the input chars out of the constructor, prepose restore to tokes, and now we call that composition stream. That's the stream we're going to parse. We're being functional here today, so why waste the lambda? Let's do this point free, the composition. All right, so now we have a parser stream object, yeah? Well, let's really push our luck with the cute purists. Let's add some properties and methods to this object. Oh no, these are purely cosmetic, right? And we rewrite our parser generator using these. Holy syntactic sugar, man. This reads almost like Python, but it's purely functional. Yeah? So now we have a reasonable parsing. So let's allow the target match to be specified as a symbol, and again, why waste the lambda? Let's just do a point 3, and let's make ourselves some parsers. Yeah? And hey, we can parse. All right, now that we have parsers, let's make some combinators, which are going to compose parsers. Yeah? First up is or else, which returns success if the result of the first if it's successful. Otherwise, it returns success if the result of the second if it's successful. Otherwise, it fails. All right? And here's some examples with PA and PB that shows it acts just like we would. All right? Next up is if then, which runs the first parser. If successful, it runs the second parser on that result. And if it's successful, we return its result. Okay? So we're running in succession now. We see that that works just as we described. However, the output only shows the result of the second parsing. More often, we'd like to have accumulation of the parsing results. All right? So, no problem. No problem. We change if then to and then. Instead of returning the result, we merge R1 and R2, and merge reaches into S2 and modifies the output to join the results of the first and the second parsings. And now we see, if we run in, then we have the accumulated results. Okay, so now we're in business. Let's turbocharge combinators with the power of functional programming using reduce Unfortunately, Q doesn't seem to remember the signature of the projections, so we have to put in a filter function, it's in the book, that says the combinator is a function of 3 variables projected on the first 2, and now reduce marked format. So we call reduce across a bunch of else's choice. We call reduce across and then sequence, and we call reduce over if then pipe, since we're just feeding the outputs in the string. All right, and we have a bunch of examples here that show that they all work just fine. Okay, first Q-test question. Explain why this naked combinator produces something that's a neutral element for if, then, and then. All right, and we know that. So the optional combinator runs the parser and returns success whether it succeeds or fails, but it captures the result if it succeeds. Okay? And here's a typical example. We're going to capture a B if it appears between A and C. Here it is, and here it's not, and it succeeds in both cases. Yeah? The required combinator runs the parser for success or failure and doesn't modify the input. So the typical use for that is it's hard to do this standing. The typical use case we require. Yeah, page, my bad. All right, thank you. All right, so the typical use case for that is we will capture A only if B is present. Yeah? All right. Now we're going to capture consecutive instances of a parser. So many will do that by iterating over the stream. Yeah? We add a temporary variable to our object, a continuation flag, and we add its properties and methods. And using that, we continue the iteration and merge the results as long as it's successful. When it fails, we stop and we remove the temporary item. Yeah? Q-test question. Explain why the difference between 1 or more occurrences and 0 or more occurrences is just the setting, the initial setting of the success flag. Okay? So some examples to show you many one, work as well. Okay? Now we're going to introduce one more parser generator, very versatile, called satisfy, which takes a predicate, applies it to the first token in the input stream, and captures it as true. Okay? We use this a lot, right? And so, simple enough. Yeah? And now we define our real symbolic parsers and character parsers in terms of satisfy, and again we do it all for. Now, we could continue to show other things, but this is all we're going to need for the second part of our demo. Okay? So now we're going to address some limitations that we have in our parser. Namely, all we do is take the branches and put them in the output stream. So in order to remedy that, we're going to add a few fields to our base object. We're going to add a tag field, which is a list of symbols and parallels the input field. And we're going to add a box, which is not checked and doesn't participate in the parsing. Stay tuned for that. We define an extended constructor for this extended record. We redefine the original constructor in terms of this one. And we notice that because we were careful to define all of our properties and methods only in terms of fields that were touched, everything works unchanged. Okay? The second change we made was we added an event handler H to every parser generator that would trigger upon dash. Yeah? And so it's no magic here. Instead of returning the result, we put the result in the found tokens into the handler and return entries. Yeah? Now we are going to use a tag handler in what we do following. And so maintain is a higher order function that returns a tag function that puts a copy of the supplied symbol into the tag field for each found token. Yeah? And so we're going to integrate that into our parser generators, and it turns out we don't really have to do anything. It just goes through until we get down to merge, and then the only change we need to make for merge is we include the tag in the aggregation. Yeah? By the way, anybody recognize a line from monad in this merge function? So everything just follows through. We don't have to do anything. We'll show you how to introduce one new parse generator, how easy it is to do this using few primitives. So we'll do a take primitive, right? And two things to point out. A, we don't want an empty take, zero take to fail on an empty string. And B, we don't use take, we use sublist because it has better semantics when it's not an empty take. Alright, now we actually have enough. There was a little more effort we could write adjacent first, believe it or not. But that would be work. And we don't want it. Holy curly keys, Batman. That looks like tie. Yes, and in 10 minutes, we can read tie. Alright, so tie does not use an alphabet. It uses an alphabeta in which consonants are king, or primary, I guess I need to say these days, and vowels decorate consonants. Yeah? So we go out and we get the hexadecimal block for tie. We get the hexadecimal block for time, and we put it in the table because we're here. Yeah? The ID field you see here first is the official Unicode name for the glyph. We store the offset in the type block as org. We store our own type designator, C for consonant, B for vowel, and we then take this table, we key it on ID and on glyph, and we call it graphic. So we pull up 44, yes, count them, 44 consonants out, and put them in their own table. The idea is to form key back in the graphics. We store a bunch of genetic information about the consonants. It will help us know how to pronounce them, make syllables. And in particular, we use the International Phonetic Alphabet notation for how a consonant is pronounced at the beginning and the end of the syllable. Yes, they are different. Nothing's easy. All right. Vowels. Vowels are really complicated in time. I had a full head of hair as we started this project. All right. I don't know if you can see this clearly. It looks like it's going okay. Vowel glyphs can appear after, before, above, below, or all around the vowel. Holy vowel movement, man. So it turns out that the glyphs appear above, below, and after, all appear after the consonant in a canonical order. So that's what we turn here in the pre, post 1, post 2, post 3 fields, along with some genetic information and the idea of pronunciation. Okay. Wow, that was a weird plan. We'll have to resize this so you can see. Alright, now we have consonants and we have vowels, so let's parse some time. It's very hard to do still. So this again is all log. First thing we do is we modify our tag function to look up the offset and append it to the provided symbol. That way we reconstruct the original from the tag. All right? And then we write our first tie parse generator that matches the character based on the ID, handy when we can't read tie yet. All right? So we do that by looking up in the reference table, and here we go. We say, find the tie fa character and tag it with IC for initial consonant. Here we make a sequence where we say find fa followed by the 7 tag it as a vowel. Hey, we just pressed our first syllable. Deep aside, it turns out the time will insert English characters midstream, so we have to know how to deal with that and do it gracefully. So we go back to our UTF deconstruction. We actually decode the actual Unicode value, and then we check to see if it's within the time block. That enables us to say Do we have a type character? Do we have a non-type character? Fundamental to us will be parser generators that match on one or more of our type columns. All right. Primary amongst those is the type character. Chi is the tonal language, which means every syllable has a pitch inflection, 1 of 5, which changes the meaning. So let's look at the type characters. Those look a little familiar? Tilt your head a little bit. Yes, these so-called Arabic numerals actually originated in India, and Thai used them when it became the first language to have written tone marks. Okay? They are always optional. Alright? So here is a sequence of find our initial consonant again, find an optional vowel, followed by our opposite tone, followed by our consonant. And you see here, in this case, we found the tone mark, and in this case, we didn't. Alright, so every consonant, every syllable in Thai has a consonant, starting consonant, and vowel. So let's start with the consonants. It's single hard consonants, which we type as C. We make a parse for that. We separate out the shape-shifting on, and because they can be consonants, vowels, parts of vowels like that. So we put these back together again as ICC. This is how you build complexity from bottom up with combinators. Yeah? We can now use ICC to pick out and capture initial consonants from actual syllables in our Thai string that we want to read. Yeah? Alright, now Thai line English has consonant clusters. Purely by coincidence, our sentence doesn't have them, and leave them here just so that you can see again how we build complexity bottom up. Yeah? Final consonants are just like this initial consonants, but they're easier. Now remember, some Thai vowels are optional. This means that you can have consecutive consonants. Fortunately for us, we only need two cases here. Find 2 of them in a row, or verify the second and capture only the first. Yeah? So now we can reassemble these various initial symbol parsers into higher order parsers that operate depending on the context. It's extremely flexible. Now, given that vowels are all around the consonant, our best strategy is to deal with each vowel separately. So we make a generic vowel parser. And so here's how we could use it, for example. This is a vowel sequence. It starts with initial consonant, followed by vowel and optional tone. So we just do that for all vowels, all syllables in which the vowel goes appear only after an initial consonant. There's a lot of them. Notice how easy it was when I had to pick one of them out and deal with it as an exceptional case. No refactoring, when we do things bottom up. Then we do the same thing when the vowel has it before the initial consonant. There's a lot of those. Yeah. And now we can put the initial consonants all together and call it, and vowels, sorry, and we can call it CVDIM. And C and VDIM, these will actually parse the heads of all the consonants in our Thai sentence. Yeah? Now, syllable disclosure is the hardest thing in Thai because of the inherent vowels. So I don't have time to go into it. What I'll say is we take all of the lexical patterns that indicate language syllable and we put that into a C-called list. We actually only need one funny named pattern that will capture the final consonant, and that says if the next token in the input stream does not start above from a syllable, but the following one does, then we capture it. Yeah? And so we put those all together along with the default of taking 0, yeah? In case things fall through, and we call that FCD. Now we sequence C and B did, and FCD, we call that syllable. We can now capture all the syllables in our Thai string. Yeah? There's some examples. All right. Now, what do we do with the syllables? We're still just putting them in the output queue. So what we do with them is ox to the rescue. Yeah, remember we put that ox in there and didn't do anything with it? So we take the syllables, make a record out of them, enlist it, and append it to the ox, which is initialized into this. How sneaky. We're creating a syllable table right under the nose of the parser. We initialize the other things to be ready for the next syllable. Now we pipe syllable through NSA because we want to get the side effects. We call that syllable dim, and we ask for many copies of it, and we can now do syllable breaks for our entire string. Alright, and we have any code. Now, clearly we're going to write some code here when we have to do words. and transcriptions, since we have to break things out, we have to find things. So the key thing here is find word. Right? The strategy to find word is to, starting at any syllable, we look for the longest word starting there at the beginning. When we do that is we iterate over syllables. We start with a syllable, we put it into a provisional word, it's an understand thing, and we ask the dictionary, yes, that dictionary. Do you have a word that starts with this provisional word? In other words, that's a stem, right? If it does, so here's that call, right here, is it a stem? If it does, then we crank the wheel for iteration that goes around and then adds the next syllable. We keep doing that until it fails and we realize we just passed the maximum word that we can understand. Yeah? Now, I've skipped over this get expanded syllable. That's where we take the syllable and break it out into DNA, all the way down to the H and C flow. We don't have time to go through all that, but I thought I'd just show you one thing that's all takeable. Everything, there's no Q sequel anywhere here. None. Zip. None. It's all lookup or reverse lookup. Yeah? I want to show you how we actually discovered what the actual spoken tone is, which I call the affected tone. Now, normally in Thai, that's presented as a long list of algorithms, and my Thai instructor says, no Thai is not that ignorant. Right? So we don't do that. What we do is we code it very carefully into a key table with a compound key. We have to get the order just right, yeah? And then very carefully, when we get effective tone function, we assemble the compound key. We'll just look up the table. The time instructor card when we see that. All right, so he's dying to get the new license so we can put this up on his website. Okay, so now we have words. We're in the final stretch here. We iterate words inside word breaks. You pass the word finder function, and in each step we construct a word record, yeah, and we append that to the word table, just like we did the syllables, and we did through the iteration function, we don't state. Alright? While we're at the word level, we ask the dictionary for its idea, look and check ourselves, and at the end I thought, hey, it's a dictionary. Why don't we ask it for the first English word that it's the first English entry that it is, okay? Now, we compose a simple breaks with the word functions to get read time. And to convince you that this is not all smoke and mirrors, let's execute that. Alright? Now, I'm going to copy and paste all this because I can't type to stay with. Alright, there's the words, alright? Let's look at the table itself. It's pretty hard to see because the type lists are not fixed pitch, but it's all there. So let's pull out the IPA, okay, so we can see that. We did that in Get Excel. Alright, now, I can read that. So, D, Char, Lo, Koka, Mon, Pasa, Taita. Apologize to Thai speakers for my lousy accent. You might actually prefer my instructor's transcription. It's a little bit more readable. Hey, but for funsies, let's see what the first English entry in each one is. Hello, people of the world. We read language Thailand can. That is the idiomatic Thai translation of the sentence that I gave my Thai instructor to start all this, and it is, hello world, we can read Thai. Thank you.